This substation controls, regulates, and distributes electricity safely across cities and industries. Human engineers monitor voltage, load balance, and protection systems to prevent outages and equipment damage. And this is where we manage the primary controls. Let's head inside.
All parameters holding steady. Systems are green.
Confirmed. Initiating sector stabilization protocols.
Check the insulators on Unit 3. Looks good from here.
Confirmed. Readings are stable.
Let's double check the insulator integrity on Sector 3.
I've already pulled up the schematic on the tablet.
Temperature is holding steady at 90. Oil levels look good.
Values recorded. Moving to the next sensor check.
That matches the expected load profile. Successfully.
Confirmed. The data log conforms the trip sequence parameters.
And the transition to the new control system is holding steady. Initiating flow control protocols to compensate.
Authorize the breaker close.
Parameters reviewed. Proceed.
Executing command.
Okay, I've got the schematic pulled up. We need to check the relays with the specifications.
Confirmed. The timing values are set correctly.
Load balance is optimized across the grid. Pink side.
Welcome to the Substation Safety Overview. We're about to simulate a load change on the protection system behind me.
They've reached the checkpoint. Initiate lockdown sequence echo.
Confirmed. Proceeding to door control. The readings on the tablet confirm the transformer is operating efficiently.
That aligns with the projected load increase.
And check the connections. The readings look stable on the tablet.
Bushings appear clean and intact. Range. We can move to the next unit. And the containment systems are fully operational according to the tablet readings.
Electrical response confirms tap 8. Inspection complete.
Adjusting the reactive power flow now.
The load distribution across all feeders is balanced and stable. Output confirmed.
Acknowledged. We are good to go.
Yes, let's move inside to the control room and initiate it.
Confirmed. I'm noting the visual inspection results on the tablet now.
This reading confirms the clearance issue on the south transformer bank.
Agreed. And visually, the alignment on these insulators looks stable for now.
Ensure all connections on the bus bars are torqued correctly.
I've double-checked the readings. Everything looks secure. Look at the spikes on the 335 feeders.
That's higher than the projection in the load chart. We need to adjust the relays.
Increasing here. Yeah.
We need to adjust the distribution flow to meet that spike immediately.
The camera cuts back outside to a low-angle shot of reclosers installed along distribution lines, designed to isolate faults automatically.
The simulation is active. Look at the differential current readings.
It is responding as expected. Ramping down the sequence now.
This system ensures our feeder stability remains optimal, even during peak demand fluctuations. Coordinating distribution adjustments now. Rotate the phasing sequencer clockwise. Confirming adjustment complete on the checklist. All clear.
As you can see, the backup feeder routes are highlighted, demonstrating the redundancy built into the grid.
Reserve capacity levels confirmed. The substation is prepared for the demand spike.
How are the readings on the main transformer bank?
Stable. Everything is operating within the safe maintenance parameters. The boundaries are secure.
Got it. And I'll double check the lockout tags before we proceed into the active zone. Lockout confirmed on breaker 7.
Verified. Authorization complete.
The readings on the tablet confirm that. We should adjust the tension before we close this out.
Elevated according to the logs.
I see it. We should check the connections while we're here.
Acoustic levels are nominal. No vibration detected on cooling units.
Confirmed. All systems operational. See this rising trend here? That correlates directly to the temperature increase we logged last week.
Yes, and it points to accelerated degradation right here on the cooling system.
Clearance reads 48 inches.
That falls within the safe perimeter.
Look at this ground connection. It's perfectly tight. Zero corrosion evident. I'll log it. checklist complete on Unit 3.
Confirmed. All tasks executed correctly. Ready for sign-off.
Looks like a phase imbalance here.
Got it. I'll reset the module now.
Initiating lockout procedures now.
This sensor input on line section 3 is showing a major fluctuation.
I'm cross-referencing the synchrophaser data now. We have a fault on the main feeder. Reroute power, sequence bypass immediately.
Reroute sequence activated. Alternate feeders online and stable.
Grid Sector 4 is back online.
Confirmed. System stabilizing across the board.
The upload is complete. Final confirmation on the site parameters.
Looks good. Encrypted channel is active. Time to head out.
This reading confirms the issue we saw on the monitors.
The tablet data aligns with the preliminary assessment. We need to isolate this section.
All right, let's verify isolation before we start. Lockout tag is in place on the main disconnect. Confirmed de-energized.
The intake valve pressure is still fluctuating.
We've stabilized the flow rate according to the schematic.
The fault source is definitely this damaged insulator hardware here. See the stress fractures.
Confirmed. Documenting the findings now for the report.
See that crack there? That's the source.
Okay, I'm logging it now. Severity level 1.
All safety steps confirmed complete. We are clear to re-energize the system.
Roger that. Initiating sequence.
This anomaly on the schematic suggests a potential instability in Sector 4.
I agree. Let's run a diagnostic overlay using the historical performance metrics.
Levels are stabilizing. Reserves look good.
Data confirms optimal readiness. Proceeding with confirmation.
The system status is green, and the robotic sequence is holding steady.
Acknowledged. I have control. As you can see, all primary systems are currently online and operational. The reactor output levels remain nominal.
Every stable light, powered home, and running industry depends on disciplined human control inside substations like this one.
He continues, emphasizing the responsibility, safety culture, and engineering precision required to manage electricity at this scale.
If you like this video, give us a thumbs up, comment below with any questions, and subscribe for more behind-the-scenes industrial documentaries.
Flawless operation. Silent flow. Power generation you can rely on, now and into the future.